Welcome back, listeners, to The Deep Dive. Today, we're plunging into, well, a really cutting-edge development, something that looks like it could significantly advance how large language models, LLMs, learn to understand us, learn to align with human preferences.
That's right. It's a big challenge.
It really is. We're talking about a brand new method called SeRA, that's S-E-R-A, which stands for self-reviewing and alignment. It was just presented at ICLR 2025 by Salix and Gupta and Saket Dingliwal from Amazon Science.
Important work coming out there.
Definitely. And at its core, this deep dive is really about tackling a fundamental problem in training these LLMs. How do we make sure they don't just spit out text, but generate stuff that's genuinely helpful, safe, and really aligned with what we actually intend?
Yeah, alignment is the key word.
Exactly. The current standard, reinforcement learning with human feedback, or RLHF, it has this well-known challenge, right? This risk of learning what they call spurious correlations.
Right, learning the wrong lessons, basically.
Yeah, learning the wrong lessons from the data. And SeRA aims to tackle that head on. As always, we're going to focus really intently on the technical details here, the implications of the tech itself. We'll steer clear of the, broader ethical debates unless they're really core to the research.
Good plan. Keep it focused.
Our mission is to give you a shortcut, a way to really understand this significant advancement.
And what's fascinating here is just how absolutely crucial this idea of alignment is for these large language models. In AI, alignment is sort of our guiding principle. It ensures LLMs don't just generate any text, but outputs that actually reflect our values, our intentions.
Right. You don't want it going off the rails.
Precisely. And RLHF, reinforcement learning with human feedback, that's emerged as our main tool for this. I mean, think about it. An LLM can generate an almost infinite variety of responses. Without alignment, it might produce toxic language, factually incorrect stuff, or just things that are totally unhelpful or irrelevant.
Yeah, useless outputs.
Right. So RLHF is the established method for teaching them these things, for getting them to generate responses that align with human-specified paradigms. We're talking non-toxic language, factual accuracy, helpfulness.
Okay, so it's about teaching it human values, in a sense.
In a technical sense, yes. Now, it's useful to contrast this with, say, classical reinforcement learning. Imagine training a robot to navigate a maze.
Okay.
In that case, the rewards are really concrete.
Right.
A number. Positive reward for reaching the goal. Negative for hitting a wall. The objective is super clear.
Mathematical.
Exactly.
Yeah.
But in RLHF, the reward is much more abstract. It's not a simple score. It's often a complex, sometimes subjective human judgment. It reflects how well the LLM's output matches some nuanced human-specified idea.
Like judging an essay versus just counting points.
Kind of, yeah.
Yeah.
It involves teaching the model, subtle preferences, tone, safety, accuracy, even style, all based on human feedback. It's a much, much more intricate optimization problem than just getting a robot to a goal.
Okay, so it's not a simple score. It's more conceptual, based on human evaluation. And you mentioned RLHF as the framework, but within that, this other method, direct preference optimization, or DPO, has become really popular. Why did DPO take off? What's its mechanism?
Yes, DPO. It really was a significant shift, a big leap in efficiency for RLHF. See, traditionally, RLHF involved multiple steps. Often you'd start by training a whole separate reward model.
A separate model just for reward.
Exactly. Its only job was to learn how to score LLM outputs based on a big data set of human preferences. Like, human said this response is better than that one, and the reward model learned to predict those judgments.
Okay, so it's a proxy for the human.
Right. And then once you had this reward model, you'd use it to provide the reward signal to fine-tune the main LLM, usually with an algorithm like PPO, proximal policy optimization.
Sounds complicated.
It is. And the big challenge was training and maintaining that separate reward model. It's incredibly resource intensive, takes a lot of time, and is frankly notoriously difficult to scale effectively, especially now with these massive LLMs and the huge data sets they need.
Right. Bigger models, bigger problems.
Exactly. DPO, though, it elegantly bypasses that whole reward model step.
How?
Instead of using an intermediate model, DPO works by directly optimizing the LLM's policy, its strategy for generating text to make preferred responses more likely and dispreferred responses less likely, based directly on the human feedback.
Okay, directly from the human preference data.
Yes. So for a given prompt, the LLM sees two potential outputs. One, the human annotator preferred, let's call it you, the winner, and when they didn't, you, the loser.
Winner and loser, got it.
DPO's loss function, the mathematical objective it tries to minimize, is set up so the LLM directly learns to increase the probability of generating EU compared to UE. It essentially gets a direct reward signal if it assigns higher probability to the winner, and a penalty if it assigns higher probability to the loser.
Ah, so it cuts out the middleman, the reward model.
Precisely. This direct optimization makes DPO much more streamlined, computationally lighter, and way more scalable than the traditional RLHF methods. And that's exactly why it gained traction so quickly. It's pretty much the standard for alignment now.
Okay, so it's simpler, faster, scales better, huge win. But you flagged that critical catch earlier, these spurious correlations. If DPO is just choosing preferred over non-preferred, how does that simple mechanism make it vulnerable to learning the wrong things? What is it about DPO that lets these biases creep in?
Yeah, this gets to a really profound point about how subtle biases can emerge, even when the optimization seems direct. The core issue with DPO, and actually many direct alignment algorithms, is that it fundamentally treats all the training pairs the same, in terms of the strength of the preference signal anyway. Meaning the reward, or the gradient signal the model gets, is the same whether the human strongly preferred one output over the other, like it was a really clear, obvious choice, or if they only mildly preferred it. Maybe it was even a tough call for the human annotator.
Ah, okay. It doesn't know how much better one was.
Exactly. DPO basically irons out those crucial differences in the strength of human preference. It only knows that one is better, not how much better, or even why it's better. And this uniform weighting, this flattening of the preference spectrum, significantly increases the risk of the model learning these spurious correlations.
Unintended patterns.
Right. These are incidental features in the training data that just happen to correlate with human preference, but they aren't the intended reason for that preference. And the model, being a powerful statistical pattern matcher, is incredibly good at finding these correlations.
Can you give an example, like the one from the paper?
Absolutely. The source material has a great vivid example. Imagine a toxicity data set. Humans are labeling non-toxic responses as preferred over toxic ones.
Okay, standard task.
Now, it's a common observation, maybe unintentional, that in these data sets, the thoughtful, non-toxic, serious responses often end up being longer, while the offensive or maybe nonsensical, flippant responses tend to be shorter.
Okay, I can see that happening.
So when a human labels a longer non-toxic response as preferred over shorter toxic one, what does DPO see? In the context of avoiding toxicity, it sees longer is better.
Ah.
So the LLM might then, quite logically from its statistical viewpoint, spuriously learn to just favor longer responses in general, even when the actual desired feature is non-toxic content or helpfulness, not just sheer length.
So it's learning the wrong feature length instead of non-toxicity?
Precisely. It's not learning to be non-toxic because it understands the semantics of toxicity. It's learning that non-toxic responses often correlate with greater length in its training data. It's picking up on an unintended, surface-level characteristic.
That's a critical technical detail. It's not getting the intent.
Exactly. The why behind the human preference gets lost. So the model might start generating these verbose, maybe overly polite essays trying to be non-toxic, when a short, direct answer would have been fine and equally non-toxic.
Okay, that makes the problem really clear. It's like DPO gets a yes-no, but human intent has this whole gradient, this how much better aspect. So if DPO flattens that and risks these unintended correlations, what's the breakthrough with SeRA? How does it actually solve this problem of models learning the wrong lesson?
Right, exactly. And this is where SeRA, self-reviewing and alignment, really makes its mark. It's designed specifically to reintroduce that gradient, that idea of strength of preference, and by doing that, limit those spurious correlations quite effectively.
Okay, how?
It uses this really ingenious, iterative, two-phase approach. It lets the model progressively refine its own understanding of human preferences by basically identifying and amplifying the clearest, most unambiguous preference signals it can find.
2 phases. What's the first phase?
The first phase is pretty standard, actually. It's like a bootstrapping step.
Yeah.
You start by doing a conventional DPO training run using an existing human annotated data set of preference pairs.
So just regular DPO to start?
Yep. This initial pass gives the LLM a baseline understanding, a rough sketch, if you will, of what humans generally prefer. It grounds the model in actual human judgments before it starts its unique self-review thing.
Okay, so it gets its initial bearings from human data, like usual, makes sense. But then comes the self-reviewing part. That's the core innovation, the SeRA magic, right? Walk us through that. How does the model generate its own examples? And maybe more importantly, how does it figure out the strength of preference for these new pairs it creates?
Yes, this is absolutely core innovation. This is what sets SeRA apart. So after that initial DPO pass, we have an updated LLM model. It has a preliminary grasp on human preferences. Now, this updated model becomes the star. It's used to generate a new, additional set of training examples. So for every input prompt, let's call it X, the model generates not just one response, but a pair of responses. A potential winner, IWA, and a loser.
And these are purely model-generated, no humans involved at this stage.
Correct. Entirely model-generated. It might use different sampling techniques, maybe just standard sampling, maybe a beam search, to get a diverse set of candidate responses. Then it somehow picks a winner and loser pair from those candidates based on its current internal policy.
Okay, it generates pairs. And then the crucial bit, how does it judge the strength of preference between them?
Right. This is the clever technical step. For each generated response, W and allele, SeRA calculates a preference score. And this score is based directly on the model's own log probability of generating that specific response given the prompt X.
Ah, its own confidence level again.
Exactly. Remember, DPO trains the model by basically maximizing the log probability of the preferred response relative to the non-preferred one. SeRA taps right into that internal mechanism. It calculates the difference in these log probabilities. Log PYWX, log PYLX.
Difference in likelihoods.
Yes. This difference represents the model's own internal confidence margin for preferring U over IL. If the model assigns a really high log probability to U and a significantly lower one to U, that signals the model itself has a strong, unambiguous preference.
Okay, so a big difference means strong preference.
Precisely. And then SeRA acts like a smart filter. It only keeps those generated pairs where this log probability difference is greater than some chosen threshold. Let's call this threshold tau.
Tau, the filter threshold.
Right. This K is key. It controls how strict the self-review is. A higher means only pairs with a very large probability difference. Very unambiguous preferences from the model's perspective get kept.
So it's filtering out the wishy-washy pairs.
Exactly. The source material has this nice visualization idea. You keep the green pairs, where the preference margin is significant and clear, and you discard the red pairs, where it's mild or ambiguous.
Like panning for gold. DPO keeps all the pebbles. SeRA only keeps the nuggets.
That's a great analogy. DPO keeps everything that might be gold. SeRA uses this PUT-based filter, examines each generated pair based on the model's internal confidence, and separates the gold nuggets, the green pairs, with strong signals from the ordinary pebbles, the red pairs where the preference is weak, ambiguous, and thus more likely to contain spurious correlations.
Okay, that filtering seems crucial for avoiding those correlations.
It is. It forces the model to focus primarily on the most unambiguous, strongly differentiated examples of preference. It ensures it's learning the intended features, not just coincidental patterns.
That's incredibly elegant. The model is its own critic, prioritizing what it's most confident about. It's generating and refining its own high-confidence preferences. Now, you said this is iterative. What does that look like step by step? How do these new high-signal samples feed back in? And what happens to the original human data in later rounds?
Right, iterative. It's a sophisticated kind of self-improvement loop. So once we've generated and filtered these new high-signal model-generated pairs, creating this refined set of model-validated preferences, we don't just use them alone. That's important for stability.
Okay, what else happens?
First, SeRA applies the exact same strong preference metric, that threshold, to filter the original human annotated data set too.
Ah, it cleans up the human data as well.
Yes. This ensures that even the initial human data, which might have some mild preferences or noise that could introduce spurious correlations, is also refined. Only the most unambiguous human preferences make the cut.
Smart. So you're cleaning both sources.
Exactly. Then you take the filtered samples from both the original human set and the newly generated set and combine them. Now you have this richer, higher signal collection of preferred-dispreferred pairs, vetted either by strong human judgment or the model's own confident self-review.
And then you train on that combined set.
You got it. You perform DPO again on this new, refined, high-signal data set. This retrains the model using data that's now much denser with strong preference signals, allowing it to learn the true human intent more accurately, more robustly.
And this whole cycle repeats.
Yes, the entire two-phase process, initial DPO, then generate and filter model data, filter original data, combine, and re-DPO repeats iteratively.
And the model-generated data becomes more important over time.
It tends to, yeah. With each iteration, the model-generated samples usually make up a larger fraction of the training data. Because as the model gets better, it gets better at generating high-quality, strongly preferred pairs itself.
It's bootstrapping itself.
Exactly. It's a powerful, virtuous cycle. The model progressively identifies stronger preference signals, its performance improves, its understanding of the true human intent deepens. It continuously generates better training examples for itself based on its evolving, more accurate understanding until performance converges. It acts as its own data curator and enhancer.
So it's constantly refining its understanding and making better data for itself. That virtuous cycle makes intuitive sense. But technically, what's the core assumption here? Why does this filtering actually work against spurious correlations? Why doesn't it just reinforce some existing bias?
That's a great question. It's not just a neat algorithm, it's based on a pretty solid insight about human intent and how it shows up in data. The core assumption is this. If a dataset is designed to capture an intended contrast, like non-toxic versus toxic, or helpful versus unhelpful, that intended contrast will inherently create a significantly greater difference in the model's internal log probabilities than any unintended contrast arising from a spurious correlation.
Okay, the real signal is stronger than the noise signal.
Pretty much. Let's go back to the length example. The probability difference between a genuinely preferred non-toxic response and a truly bad toxic response is likely to be much, much larger than the accidental probability difference between just any long response and any short response, even if length happens to correlate somewhat with toxicity in the initial data.
The non-toxicity signal is just fundamentally stronger.
Right. So SeRA, by using that threshold to focus only on pairs with a significant probability difference, is implicitly prioritizing the intended semantic or functional features over the accidental spurious ones. It's like a signal-to-noise filter. The true signal of human preference, once the model starts learning it correctly, generates a much clearer, stronger distinction internally than the noise from spurious correlations.
And the research backed this up.
It did. They tested SeRA on 4 different benchmark data sets covering things like toxicity, harmlessness, helpfulness, and in all cases, this assumption seemed to hold true. The intended contrasts generated stronger signals.
So it seems like a fundamental principle, not just a fix for one data set.
That's the implication, yeah. It suggests SeRA is potentially a more robust way to teach AI to pick out our genuine preferences from the noisy data we give it.
Okay, that's a solid technical foundation, leveraging the model's confidence as a proxy for true signal strength. So let's talk results. How did SeRA actually do compared to the standard methods? What kind of performance gains did they see? What does this mean practically?
Yeah, the results were pretty significant, even dramatic, you could say. They ran careful evaluations across all 4 benchmark datasets. They compared the SeRA-trained model against 3 baseline models, including standard DPO, to make sure it was a fair fight.
How did they compare them? Human judges.
They used an interesting approach, an off-the-shelf LLM as an impartial evaluator. For each test input, this evaluator LLM would look at the output from the SeRA model and the output from a baseline model and choose which one was better. It's a common, scalable way to approximate human judgment in these comparisons.
Okay, using an AI to judge AI and the results.
The results were really conclusive. The SeRA-trained model won significantly more often in these pairwise comparisons against all 3 baselines across all 4 datasets.
How much more often? Like a few percent?
No, much more than that. We're talking improvements in the win rate ranging from 20% up to 40%.
Wow, 20 to 40% increase in win rate. That's huge.
It really is. It's not just a tiny edge. It shows a substantial improvement in the model's ability to generate outputs that are preferred, and crucially, preferred because they're better aligned, not just because they latched onto some spurious correlation.
So practically, this means models that are more consistently on target, safer, more helpful.
That's the idea. Models that more accurately reflect the nuanced human intent that plain DPO struggles with, which should translate to more reliable models needing less manual checking or fixing after deployment.
Okay, 20–40% is definitely impactful. That suggests SeRA really is tackling a core weakness. Now, the experiments use DPO underneath, right? Is SeRA stuck with DPO, or could you use the self-review idea with other alignment methods?
That's a really important question about its generalizability, and the paper explicitly addresses this. While their main experiments use DPO, they also demonstrate, mathematically, how SeRA's core idea, the self-review, and the strong preference filtering can be generalized to other direct alignment algorithms too.
Like what?
Well, methods like KTO, Kahneman-Tversky optimization, or maybe even some types of PPO that work directly with preference data, they could potentially integrate SeRA's self-review mechanism to benefit from its ability to distill these high-signal examples.
So it's potentially a broader tool for the alignment toolkit.
It seems so, yeah. Not just a DPO add-on.
Right.
which really expands its potential impact.
Okay. Now, another critical thing with these iterative self-generating methods is the risk of, well, feedback loops, right?
Hmm.
Or mode collapse, where the model just starts repeating itself or reinforcing its own mistakes. How does SeRA stop that from happening? How does it avoid amplifying bad patterns from the initial data?
Excellent point. That's a paramount concern anytime a model starts learning from its own outputs. The classic risk is exactly that. It could accidentally amplify some bias or error from the first data set, getting stuck in this loop, reinforcing its own flaws. Or it could lead to mode collapse. The model just generates the same boring, repetitive stuff because it locked onto one narrow, maybe incorrect interpretation of what's good.
Yeah, you don't want it getting stuck in a rut.
Definitely not.
Hmm?
So SeRA includes a specific technical solution to mitigate this. In each iteration, the way the model's policy is optimized, the reward signal essentially, isn't based only on the current iteration's filtered data. It also takes into account past iterations.
How does it do that, like averaging?
It could be done in a few ways. Maybe carefully combining the current high signal samples with a weighted contribution from samples generated in earlier rounds, or perhaps using a form of regularization that keeps the current policy somewhat anchored to earlier, potentially more stable or diverse versions of the model. The paper talks about ensuring continuity in the characteristic features of the training data.
Ah, so it has a kind of memory. It doesn't just jump based on the latest batch.
Exactly. By constantly referencing or incorporating data derived from earlier states that were perhaps more diverse or closer to the original human data. SeRA prevents itself from drifting wildly or over-indexing only on the newest, potentially biased patterns it just generated. It stabilizes the whole iterative process, aiming for smooth convergence without that catastrophic mode collapse or amplification of errors. It's like a technical anchor.
That's a crucial safeguard. Stop self-improvement turning into self-delusion. Okay, so the paper covers a lot, but like all research, it opens up new questions, things it doesn't explicitly talk about. For instance, they mention monitoring convergence behavior in applications, but what does that really mean technically? Beyond just watching the loss go down, how would you really monitor this in a complex deployment? What are the challenges?
That's a really practical and deep technical question. Yeah, when they say monitor convergence, it definitely implies needing more than just looking at the DPO loss curve. That loss could keep decreasing even if the model is, say, collapsing its output diversity or learning some new unwanted correlation.
Right, the loss isn't the whole story.
Not at all. In a real-world deployment, you'd probably need a suite of metrics. You could track proxy metrics for alignment that are independent of the main training loop. So if you're aligning for non-toxicity, you wouldn't just look at the training win rate, but maybe you'd monitor performance on a fixed, curated holdout set of known toxic versus non-toxic examples. Or track the entropy of the model's output distribution. A sudden drop might signal mode collapse.
Okay, external checks.
Yeah. Or even maintain a small, ongoing human-in-the-loop validation set. People checking a small sample of outputs that aren't used for training, giving you an unbiased, even if slower, signal of actual human preference drift. Things like human agreement rate on this set could be vital.
What about looking inside the model?
That's another angle. Using interpretability techniques or feature attribution methods. Trying to understand what features the SeRA model is actually paying attention to. Does it align with our intuition? Are the outputs becoming too similar? Is it actually generalizing, well, to diverse unseen prompts, or just getting good at the specific types of examples it's generating for itself?
Lots to track. What are the challenges in doing that?
Well, defining optimal convergence for alignment is inherently tricky. It's often subjective. And the computational overhead of running all these checks continuously during an iterative training process, especially for huge models, is significant. You need to balance how thorough your monitoring is with how computationally feasible it is. It's a tough engineering balancing act.
Right, always a trade-off. Okay, another technical detail. SeRA hinges on filtering pairs where the preferred one scores significantly higher. That threshold, what does significantly mean mathematically here? Is it a fixed number? Does it adapt? And how sensitive is the whole process to getting that threshold right?
Yeah, the exact nature of T is crucial. Significantly higher needs quantification. The paper gives the concept, but the practice could involve different things. It could be a simple, fixed, absolute difference in the log probabilities. Like, the difference must be greater than 0.5 or 1.0 or whatever you pick. A higher 2 means a stricter filter.
Okay, hard cutoff.
Or it could be more dynamic or statistical. Maybe for each batch of generated pairs, you calculate the mean and standard deviation of all the log probability differences. Then you set to be, say, 1 or 2 standard deviations above the mean for that batch, using a z-score, essentially. That would make the threshold adaptive.
Adapting to the model's current confidence levels.
Right. Or maybe even more advanced methods, like using anomaly detection to find the real outliers in terms of preference margin.
And how critical is getting this right?
Oh, it's absolutely critical. Super sensitive. You set too low, you don't filter enough, you let too many mild ambiguous pairs back in, and you risk reintroducing the spurious correlation problem SeRA is trying to solve.
Undermines the whole point.
Exactly. But if you set too high, you might throw out too much data, including potentially valuable signals that were just below the threshold. That could slow down learning, maybe make the model less diverse, or even cause it to overfit to a very narrow range of super confident examples.
A fine line to walk.
Definitely. Finding the optimal would require a lot of experimentation, hyperparameter tuning, ablation studies, seeing how different values affect win rates, convergence speed, and the final model's robustness against spurious correlations. And you'd have to ask if chat should stay fixed or change during the iterative process as the model gets better. It's a key tuning knob.
Fascinating. So it's a carefully calibrated filter. Okay, let's zoom out a bit. Could this core idea's self-review, filtering for strong signals, apply beyond LLMs and human feedback? Could it work in other areas of RL or machine learning where spurious correlations are a headache? What would need to change?
That's a really powerful question about generalization. And I think the core principle does have broader appeal. The underlying idea that intended, meaningful signals often produce stronger internal model responses than accidental correlations feels quite general.
So maybe in computer vision?
Yeah, imagine a vision model learning spurious correlations. Like, it identifies doctors, mainly because they often have stethoscopes in the training images, not based on other features.
Right. The stethoscope becomes the signal.
You could potentially engineer a self-review mechanism. The model generates variations of an image or analyzes feature importance. It could then prefer examples where the intended feature's face, attire, context generate a strong internal response difference, while downweighting examples where the difference relies mainly on the correlated artifact, the stethoscope. The preference isn't human-labeled, but an internal measure of feature saliency or discriminative confidence.
Okay, adapting the idea of preference. What about classic RL, like robots or game agents?
There, too. An agent learning in an environment could identify states or action sequences that lead to consistently, significantly higher rewards, unambiguous positive outcomes. It could prioritize learning from those strong reward transitions, rather than from situations where the reward difference is tiny and might just be noise or related to some irrelevant feature of the environment state it observed.
So redefining strong preference for different domains.
Exactly. You'd need to translate the concept of log probability difference into domain-specific metrics, maybe using attention maps in vision, analyzing latent space geometry, or looking for statistically significant reward differences in RL. It's about finding that clear, strong signal of the intended objective amidst all the other noisy correlations, whatever the data modality is.
That's a really interesting potential future direction, taking the core logic elsewhere. Now back to LLMs and practicality. DPO is scalable, good, but SeRA adds this iterative self-generation and filtering loop. How much does that add to the computational cost, especially for the absolutely massive models we see now? Are there implied optimizations needed to make this work at scale?
Yeah, that's the million-dollar question, or maybe the multi-million-dollar compute question. DPO is more scalable than old-school RLHF, true. But SeRA absolutely adds layers to the process. Each iteration involves several heavy steps.
Like the generation step.
Exactly. Using a huge LLM to generate new response pairs for potentially millions or billions of prompts. That's a massive inference workload just by itself. Doing that iteratively adds significant cost compared to just one DPO pass.
And then there's filtering and retraining.
Right. Calculated all those preference scores, filtering both the generated and original data sets, and then running another full DPO training cycle on what might be an even larger combined data set. It all compounds. It means longer training times, more GPU hours.
So how do you make it practical?
You'd need serious optimizations. Things like efficient sampling strategies. Maybe don't generate pairs for every prompt, but focus on prompts where the model is currently uncertain or where spurious correlations are known to be a problem. You'd absolutely need distributed training frameworks that can handle orchestrating the generation, filtering, and training across potentially thousands of GPUs in parallel.
And data handling.
Critical. Highly optimized data pipelines to filter and combine these massive data sets quickly, avoiding I/O becoming the bottleneck. Hardware-wise, maybe it pushes towards accelerators that are even better balanced for both high-throughput inference for generation and large-scale training for DPO.
So it's a trade-off. Better alignment for more compute.
It definitely looks like
Yeah.
that. The engineering challenge is finding the sweet spot. How many iterations do you really need to get robust alignment without the costs becoming prohibitive? Minimizing the overhead while maximizing the alignment benefit.
A classic engineering problem. Okay, one last deep dive area. The nature of these spurious correlations. Can SeRA tell the difference between a bad one, like the length example, and maybe a good latent feature the model discovers that just happens to correlate with preference? And how well do these internal model probabilities really capture complex, subjective human preferences anyway?
This really pushes into the subtleties. SeRA works because it assumes the intended contrast signal is stronger than the unintended correlation noise. It's best against spurious correlations where that assumption holds.
What if the spurious correlation is really, really strong in the data?
That's the tricky case. If a bad correlation is so pervasive in the initial human data that it also generates a large probability margin, SeRA might actually amplify it, mistaking it for a true strong preference. Imagine if, I don't know, every single helpful response in the dataset accidentally used a specific polite phrase. The model might learn to strongly prefer that phrase via SeRA, even if helpfulness was the real goal.
So it's not foolproof against all types? How could you even tell?
Differentiating that technically is hard. It might require post-hoc interpretability looking after training to see what features the model actually relies on. Does it make sense? Does the model generalize if you test it on data where that correlation is broken? Can you trick it with adversarial examples designed to exploit the spurious correlation? That's active research territory.
And what about subjective preferences, like judging humor or creativity? Can model probabilities capture that nuance?
That's where the mapping gets really fuzzy. Model probabilities are statistical likelihoods based on data patterns. Human intuition, especially for subjective things like humor, creativity, empathy, is vastly more complex, context-dependent, maybe even inconsistent sometimes.
Yeah, humans aren't always logical statistical machines.
Exactly. So SeRA leverages the strength of the model's internal preference signal, which is derived from those patterns. But it's still fundamentally learning from human labels, often simple binary choices. This is better than that. The model's internal confidence might not perfectly align with the intricate reasons why a human strongly prefers something subjective.
So there could be edge cases.
Definitely. Edge cases where the model shows strong preference based on its probabilities, but still misses a subtle human distinction, especially if that distinction wasn't clearly represented by a large probability difference in the training data it saw. This really underscores why we still need continuous human oversight, robust qualitative evaluation, maybe even alignment methods beyond just pairwise preference to truly get these models aligned with complex human values.
That's a critical point. Even with smarter self-review, the model's world is its data, and human subtlety is hard to capture fully. Okay, let's wrap up our deep dive. Connecting this all to the bigger picture, it feels like SeRA offers a really elegant, technically sophisticated solution to a persistent, tricky problem in LLM alignment. It seems to push models significantly closer to really understanding and reflecting our nuanced preferences, not just surface correlations.
I agree. We've seen how SeRA takes on spurious correlations, especially within DPO, using this innovative self-review and filtering mechanism. By getting the LLM itself to generate and then strictly vet data based on internal confidence, it amplifies the strongest preference signals, leading to more accurate and robust alignment. And those 20% to 40% performance jumps are serious evidence of its effectiveness.
It really makes you think.
It does. And it raises this important question for you, the listener, to consider. As these models get better and better at self-reviewing their own outputs for quality and alignment, what new possibilities open up for more autonomous model development? How might this shift toward self-improving alignment change the whole landscape of human-AI collaboration, especially in areas where we currently spend huge effort on manual data labeling or rely on fuzzy human judgment?
That is a powerful, forward-looking thought to end on, thinking about the future of AI development and our evolving role in it. Thanks for joining us for this deep dive into SeRA. To stay updated on the latest research like this, remember to visit our webpage. The link's always in the bio. Until next time, keep exploring.